Good afternoon. We're going to get started with Nara, Khou, and Cort Lunke from Land of Lakes presenting on self-service geospatial analysis leveraging Databricks and Apache Sedona.
Oh, perfect. Thank you very much. You can see we really coordinated outfits well, right? I'm the PC, he's the Mac, if anyone remembers those commercials. We really appreciate everybody coming out or watching this virtually. And everyone in person, thanks for hanging in there today and attending one of the last sessions of the day. We'll try to make it worth your while. We'll talk a little bit about the company. We're both from Land Lakes. We'll introduce ourselves. Then we'll talk a little bit about why we think geospatial is such an important topic to have represented out here at Summit. Then we'll give a little bit of an overview of a business problem that we had to solve that we thought was interesting and architecturally significant, and the importance of building it out on a unified platform that is Databricks. Then we'll talk about how we extended Databricks with spatial capabilities leveraging Apache Sedona, open source top level ASF project, and some R visualization libraries. Finally, we'll walk you through a demo and some code. Basically, the production workloads that we have sort of pared down and made shareable using sample data. We were going through the summit materials for the year, and we got excited because there's a lot of talk about lakes and lake houses, and we're based out of Minnesota, so we spend a lot of time on the water. We have over 10,000 lakes. We're the experts on lakes, but then we land out here, and we learned that it's a different kind of lake they were referring to, so we had to quick put together something data-centric, but luckily we were able to do that. My name's Cort Lunke. I'm the reporting and analytics lead for Truterra. That's a sustainability line of business for Land Lakes, promoting sustainable programs in crop and livestock operations. Hand it over to my colleague, Nara.
My name is Nara Khou, and I'm the lead data engineer for Truterra. And I've been working with Hadoop since 2012, where we had to write MapReduce using Java, and back then we were running models for Spark, also developed in Java, which was very, very convoluted back then. So things are so much easier now. Like the kids these days, you can just spin up Databricks. Back then we had to worry about which rack the server and stuff like that was in to try and get as much performance as we can. So this is our team. One of our engineer who couldn't make it out here, he was also part of the project. That's Joey, and then our manager who let us be out here. So
our fearless leader, yes, sir. So show of hands, how many people are familiar with the Land Lakes brand? That's awesome, very good. Thanks for attending. Maybe you already know this, but we're big. That's a key stat, big, very big. Tend to hover around Fortune 200, kind of changes year to year. We operate in all 50 states, 60 countries, just shy of 20 billion in revenue. Not only are we big, we're influential. I have to plug that. We were just announced as part of the Times 100 most influential companies of 2023, so we're honored to receive that distinction as well. We're also a member-owned cooperative, and what you find, or at least I find working at Land Lakes for as long as I have, almost 10 years now, is this really permeates the culture in a very positive way. Our member owners are dairy farmers, they're ag retailers, and the farmer network that they interact with, and everything we do at the company is for them, is for the farmers. We also have very, I would say, wide and in-depth view of the farm-to-fork food supply chain. Everything that happens within the farm gate, all the way to the butter served at your dinner table, and everything in between. That's crop inputs, that's the seed, fertilizer, and other adjuvants and things that are applied to grow crops that then feed the animals that then produce the dairy products and other pieces. We're also heavy on the R&D side, and with Truterra, also implementing sustainability programs across the country. So that's a bit about Land Lakes. Why did we put this spatial content together for the group here? Why did we think that was important? Well, raise your hand if you've worked with spatiotemporal data at some point in your career. Yep, all the raw observations that we look at tend to occur at a particular point in space and time. And yet we find that even though geospatial data permeates all of the problems that we're trying to solve, it's really still a difficult and niche skill set to find. It's also very difficult to find support for it in the enterprise platforms that we use. So that's where, to meet our business needs, we had to deviate a little bit. We'll talk about that. What particularly makes geospatial difficult? Well, first you have to pick a coordinate reference system. You have to get a geographic representation of the Earth that sort of fits your need. You have to pick the right projection when it's laid out on a screen or when it's used for map visualizations. And there's a lot of different options, and it's not always clear what you should go with. Additionally, there's a whole different set of file formats, some legacy, some newer, that you have to interact with, as well as geographic information systems, as well as data structures, geometric types and features, things like lines and polygons and points. But there's also sort of another complexity in having to index geospatial data such that you can performantly query it. And finally, there's a different set of functions used to operate on that data geometrically. So to summarize, it's not enough to be a data engineer necessarily when working with geospatial data. You also have to know a bit about geography, a bit of mathematics, especially geometry and related disciplines. And finally, you have to have a good head for data analysis, sort of crafting a spatial, more or less localized narrative for the insights that you bring. We'll talk a little bit about the need for a unified platform-based solution at this point. So to put the group here in our shoes, working for Truterra, it's a relatively new line of business. We've been in operation for several years at this point, but when we joined the team, they had just sort of implemented their transactional app for collecting data on field operations, realized they needed to do some analysis on that data, and like many of you have probably done throughout your career, they went with a cloud SQL-based solution, sort of an OLAP database as their initial foray into data analysis. However, it didn't stand the test of time. It didn't have the capabilities or the scale that they needed, so they brought in some additional skill sets, and myself and Nara and some data engineers, and we were tasked with sort of modernizing their data platform. As part of that, they had some pretty big asks for a relatively new team. One of those asks was analyzing farm operations and their impact on the water supply, on watersheds throughout the country. So these are custom geographies. Additionally, we deal with a lot of field boundaries, talking about corn, soybeans, specialty crops, that again, we can relate to their geometric objects as well as public data sets that are also typically aggregated at maybe the county or the census tract or the watershed level. So, of course, when they asked us if we could do these things, we said yes, because we're pretty confident in ourselves, and we were excited to try and solve those problems. So we started exploring Databricks compatible options for geospatial, and of course, Apache Sedona, one of the strongest offerings in that space. We'll talk a little bit about the platform that we deployed, not too much. We do want to treat spatial capabilities as sort of a first-class member in the back-end architectural features that we provide to the business, along with the data preparation and integration and all that. We do call that out separately. It's so important in the agricultural space. Additionally, then, we have, I would say, fairly elegant, but maybe vanilla Azure and Databricks implementation. So you can see we have cloud storage accounts, of course, mounted that to the Databricks file system. We took a special interest in security and automation, so we have CI/CD processes to deploy all this. We have a lot of different data sources that we have to integrate with, and some other sort of Azure tooling, Power BI for business intelligence, and Data Factory for integration that we use in tandem with Databricks. But really, Databricks provides nearly all of our compute except for some data collection that we run elsewhere. All right, so next we'll look a bit at what Truterra does and the problems that we're trying to solve before getting to the demo. So we have nearly 8 billion people on the planet. That number is growing, and food is a problem. Getting food produced and where it needs to go to feed that growing world population is of the utmost importance. It's a global problem. Farmers are a critical part of the systems that feed that growing population. I would argue the most critical part. Farmers are also a critical part of the solution in the sustainability challenges that we face globally and here at home. But farmers are running a business, first and foremost. An ag operation needs to be profitable, so it's not enough to go to the farm gate and suggest sustainable practices if it doesn't help their bottom line. So that's what Truterra does. We ensure we have best-in-class sustainability programs that first and foremost benefit the farmer, benefit the operation, and lead to long-term operational health for the grower in terms of soil health, in terms of irrigation, as well as help profitability, either by introducing the farmer to new revenue streams or reducing their input costs, maybe by precision application of different products, reduction in products used on the field while maintaining steady yield does reduce the footprint of that operation if you think about the manufacture of fertilizer and other crop inputs. Truterra offers several different programs to growers. First, that comes to mind is helping them into the carbon market. That would be carbon reductions in their operation due to sustained practice change on the field, as well as carbon removals. The act of farming removes carbon dioxide from the air, sequesters it in the soil. That's all monetizable for the grower. Additionally, we collect that farmer to downstream food supply chain partners that potentially process those raw materials into some other product. These are big food and bev companies, or even textiles, that have a vested interest in investing in sustainability. That would serve to promote insets within their supply chain over time, show sustainability improvements for these large companies. We make sure that the farmer gets some of that value and that those practice changes happen at the farm. As far as practices go, a lot of it comes down to tillage and cover crop and fertilizer and irrigation, as well as what is planted in terms of the primary crop and nutrient management. The other piece of this is we monitor and verify that data over time. We model the sustainability impacts that the operation has, as well as different KPIs such as carbon, such as erosion, such as soil quality. We also connect growers with that data that we collect with potentially local conservation initiatives in their counties or municipalities in which they operate. One of the types of programs that we try to connect them to is water quality, right? It's very important to have clean streams and rivers and lakes for the local water source. So that's where some of the custom boundaries that we use to aggregate data come in. In this case, watershed boundaries. This is publicly available data hosted by the USGS. Essentially, for an area, it sort of classifies where drainage ends up in that area. It's broken down in sort of a hierarchical tree structure. In this case, we can look at the state of Minnesota. This is what we use for the demo. Of course, we have 87 counties in Minnesota. We have very large two-digit watershed regions across the country. There's 4 of them that overlap with the state of Minnesota. If you drill down into 8-digit watersheds, we have 81 throughout the state. And if you go all the way to 12-digit watersheds, we have about 3,000. So you can really traverse very broad or very localized watershed regions when you're targeting field practice improvements that could improve water quality. It's a big part of the demo. We'll be looking at the headwaters of the Mississippi River watershed up near Itasca State Park in Minnesota, if anybody's been. Last thing that I want to call out before I hand it over to Nara here to go over some of the demo is really opening up the geospatial door. And the analysis that we do really opens up the opportunity to bring in other public data sets, which, as I alluded to, are often also geospatial by nature. So we use several public data sets. We'll demo a couple of them today. All right. So over to Nara here.
Yeah, so getting started with Sedona and R. So why did we choose Sedona, right? We were looking for something that is very interoperable with Databricks and Spark and scalable. So Sedona fits that purpose. It has great spatial features and a great development communities. It's also very compatible with various languages that we're using, like R, Python, and SQL. So having worked with it, we know that it's easy to use, it's high performance, and it is continuously improving. And I guess quick shout out, congrats to them for making it to the top level ASF. And Cort is super excited to say that he had used them before they were cool.
Cool.
So, we interact with Sedona as more of like a user, not hoping to do more, but currently we're mostly using it. So, and this is big news. So Sedona, I think became private or got spun off for a company called Veribots, and they just released kind of like a no-code deployment onto Databricks, and which we didn't know about. It was recent when we were using it, we had to kind of do the deployment ourselves. So that's what we'll show in our demo.
Very, very recent news, but
Yeah,
they're the real
today.
deal. The creators of Apache Sedona and the development community, if you look at who's contributing to the Sedona project, a lot of great engineers from several different great tech companies. But congratulations to Werobots as well.
Yeah.
Very successful round of seed funding, and this is all sort of breaking news in the last month. So just wanted to give the shout out.
Yeah. So for our demo, we'll go through kind of like our cluster setup, downloading the public watershed data, and like how we use it to show like spatial mapping. So starting with the cluster, the cluster size kind of matter a little bit, especially the driver node, especially on how we're using it. Like some of the processes only really run on the driver's node. So you'll see it in the video, what our cluster configurations will be. And as part of the setup, this is what we were saying. We had to do some custom loading of the libraries. So we would download the jar files and then loading it onto the cluster nodes, like the drivers and the other cluster nodes, via init scripts. So that way we can make use of Sedona on Databricks. I guess this is mostly kind of like how we think about where we want to install packages. So like, with Databricks, you could install packages at the cluster level, or you could do it within the notebook. So for us, the criteria is mostly kind of like if the package will be used across multiple engineers, multiple projects, and maybe we'll install it on the cluster itself. Versus if they are more kind of like single use, more for just a particular project, or then we can install it just within the notebook. For this project, we actually make a use of a combination of both cluster installation of packages and notebook installation, mostly our notebooks as well. So I thought this would be worthwhile to show. This is how we configure the libraries in a cluster. We did a one-time download of the artifacts for Sedona. And then we have two scripts to copy those jar and loading them onto the cluster nodes. And we have a script for installing and updating like our libraries dependencies. So this is a screenshot of our configuration, like the Spark configuration, to enable the use of Sedona. And then you can kind of see the init script. So one thing to note is that like we're putting the init script in the workspace, and this is important because it allows for like ACL's control of the file. So like, you don't necessarily want to, if you just put it in the plain dbfs location, then there's really not much, permission control over that, so.
All in all, a very smooth process. A lot of this is in the setup docs as well for Sedona, so if you ever need, worked very well.
Yeah, and then we have our library dependencies installed there for Sedona and GeoPandas. And we'll move on to the data pipeline. So this is kind of like the workflow that we have. Data collections. We'll show like the download of the public data for the water boundary, generating like our demo fields and saving it off. And then we'll do some data preparations. Where we would enrich the data more for mapping and visualizations. And then we'll show the analysis steps that we're going through, and we'll show the data visualizations. And kind of towards the end, we'll show kind of the user experience, like how our business user would log in to get this data. So basically, this is our process from collecting data, kind of like an overview of it, into aggregating the data and displaying it. So do the code walkthrough, and hopefully this will. Oops, we want to do.
Yeah, part of the reason, too, we thought this would make a decent demo for the summit, it's just so well contained within Databricks. We don't have to leave the unified platform for any of this. We just have to extend it with Apache Sedona. And from a user experience perspective, there's a lot that you can do, we found, without leaving the notebooks.
Yeah.
So like give read-only access and have dynamic widgets, things of that nature.
So we wanted to do like a live demo, but we were kind of scared of that, and then so we decided to kind of like record the video to go through it.
We've made our environment too secure. I don't think we could have gotten on it from the Summit Wi-Fi out here. So. Yeah.
So this is the first part. This is basically showing what we've done. The first part here. These are kind of like the free script that we're doing. So we're grabbing the Sedona jar files, and then this is creating the shell script to move the jar file to the correct location.
I'm going to kind of control it when you talk.
Yeah.
Okay.
And then, so this part is we're installing the needed R libraries for there.
Yep.
And then you can kind of take a look here. It's kind of like our cluster configuration. So you can see like the driver node is a lot bigger memory, and it's just more powerful in general. Like certain things, like especially with spatial, it is it's not distributed yet. I guess at this point when we're just downloading the geo database file and trying to transform it.
It's hard to distribute
yeah.
Inflating a zip file, So
yeah. So
a lot of it we do on the driver for the demo.
Yeah.
This is just a review of the cluster configuration. Really, I might skip ahead a little just to save some time.
That's
here.
true. Because we're running out of time.
Yep.
So this is, this section is essentially just downloading the USGA, the field boundary, and then extracting it, and then converting it to shapefile, so that way we can read it in and create the Sedona data frame, and later writing it to the Databricks data frame, so that way we can store it into Delta as a Delta table.
Yeah, interoperability is another tough thing to solve sometimes with spatial data. So, and of course, all of the output goes to cloud storage. At this point, it's just a geo database, again, hosted by the USGS.
So in this section, we're basically just kind of splitting the layer into the different hugs like level, and then creating the shapefile and then saving it off for later processing. So I want to skip ahead maybe. Again, we're saving this into our cloud storage account.
This is where we finally see some spatial operations from Sedona. This is when we'd actually be translating those shape files that we, the layers that we extracted from the Geo database and transformed into shape files for GeoPandas interoperability. You see we explicitly set the schema for those watersheds to include the geometry, which is a Sedona geometry type, user-defined type. And finally, we can instantiate a Sedona data frame from those spatial types. So there's some attributes related to the boundaries, and then we have the watershed boundary as a column. Attribute include the area in acres, as well as the watershed name and the ID, basically.
Yeah.
We can then enrich those boundaries that we have. We take the bounding box, xmin and xmax, ymin, and ymax coordinates. It's useful to sort of set the size of your map visuals later on. We also enrich it with the centroid using some fairly straightforward Sedona user-defined functions there. So those functions that we registered that are implemented by the Sedona project, and then we can, of course, take a look at those tables, at those delta tables that now have not only the geometry, but a few attributes associated with.
I guess, and the other reason that we're doing the boundary is because when we are mocking up the data, we can use those to ensure that we're kind of like within the same range.
Yeah, spot on. And that's a good segue into actual sort of mocking up of the data here.
Yeah.
We have some utilities we use internally. We don't need to go into too much detail. We've just sort of defined sample data set schema in list of dictionaries. Essentially in Python, it's just a custom data set definition. And once it's defined, you see we have some qualitative attributes that are leveraging the Python Faker library to generate names. We also have some choice sort of qualitative attributes defined from Spark SQL, essentially querying that watershed table to get a list of watershed names. And then finally, some numeric values, which are simply sampled from a normal distribution with a given mean and standard deviation. Those are some of the shared functions that orchestrate all this, a lot of NumPy. We don't need to go through all of the data generation. It's not necessarily the purpose of the project, but we will take a look at the sample data set. Again, persisted as a delta table.
Yeah.
We also generated random boundaries within the watersheds for those fields so that we can demo the duplicate detection spatial joins that we do, looking for primarily field intersection to try to gauge where duplicate fields might exist in the system. Very important to the business problems that we're trying to solve, that we don't double report on any acres.
Yeah.
These field boundaries could be stored in mini systems that we integrate with, and we need to make sure that we're deduplicating on the back end. And finally, we see the sample data. This is all generated again. These aren't real farmers, they're not real fields, just sampled for this demo. We also calculate the area for different fields, and to sort of showcase some of the Sedona functionality, we also validate that against the known acreage for the watersheds. So to sort of double check our logic. But you see we're transforming the coordinate reference system here from a sort of degrees-based to a meter-based CRS, such that we can then apply a conversion factor, get from square meters to acres, technically. So a lot going on there, but it's really just 3 function invocations in Sedona. So, and you can see that they're all pretty much exactly spot on. Yes, good to check your work, especially if you're me, you know. Now we're actually getting into some of the dynamic notebook capabilities. We have dynamic widgets backed by SQL queries. Users can actually come in and use this notebook. We have business analysts in Databricks that do that, although they only have read-only access and they only see the results, so it's a bit cleaner. We'll get to their experience at the end. But again, once we've selected a watershed basin, we can then visualize, generate some Cort for analysis.
Yeah, and the nice thing about the widget is like we're pulling in the data from SQL and populating the dropdown. So, and the way that we have it set up, when you select one, one of the hierarchy, it re-execute the run so that way the variable will get updated. Mm-hmm. So you can kind of see that.
Yeah, spot on. We have it run all access commands. That's a widget setting then you can get if you hit the settings button here. I think we do that later in the video just to showcase. Yeah. But if we continue on, we then aggregate the data, taking a sum of some of the metrics, the yield for the field, the nitrogen applied, the acres as sample fields that we actually use in production, and essentially group them by watershed. This would be the data backing the Cort, the map visuals that you'll see in a minute here. We show those visuals in line in the notebook. We also have a downloadable zip file that contains all the images so that our business partners can easily download the whole set and put them in presentations that they show to ag retailers, to farmers, to educate and show some of the work that we're doing. Actually, the first implementation of this, our business partner said they call it field days. They were out there interacting with growers, and what she said was farmers were actually sort of leaning forward in their seats to see some of these visuals. They were so interested. So I thought that was pretty cool. Maybe it was exaggerated, I don't know. But
so this is just kind of like an overlay of Minnesota and this is the headwater, I guess.
Yep, sort of showing where we are within the state. And then here you'll see sort of a zoom in on just that upper Mississippi watershed with aggregated values. And we do 3 visuals. As you can imagine, once you have one, it's fairly easy to get the next, so we don't need to look at every one. But here would be an example we'll show this again from the user perspective. So this is saving, this is nitrogen by watershed, and finally the downloadable artifact. You see actually in line in the notebook, they can just click that zip file, which again we do as part of the demo here. Yeah, there we go. Easy enough. I know it's not quite full screen. There we go. Again, you see the sort of Minnesota view, same inline image we saw earlier in the notebook, and we see yield by watershed. And we're going to skip ahead a little bit to just very briefly show the user experience, and then we'll go back and look at some of the data quality checks. So a user here would see the results only view, and they'd still be able to change the widget values, and they'd still be able to run the notebook, and they would just sort of wait at that point to get the output. It takes less than a minute to run, so fairly good user experience with all the data aggregated and ready to go. Here's that run access command that's so important for the dynamic widgets, just one setting in the widget panel that we leverage. And again, just kind of a cleaner version, no code, no results, just the images and the file download. So, not necessarily winning any UX awards here, but having nothing, the business was very happy to have this. No issues, as you can imagine. Last thing before hopefully we have some time for questions is, sorry, I'm trying to find my cursor.
Towards the end, yeah.
That didn't, oh, there we go. Yeah, bear with me just for 1 second, and we will get to here's really a simplified version of a larger query that we run in production. That's like a Cartesian product of a self-join of all the boundaries that we have in the boundaries table. Again, looking for duplicates, so we'll see if they intersect. We do filter down. We don't need to do a pairwise boundary overlap if fields are like 10 miles apart, for instance, right? No field's going to be that big. So we do it a little smartly to sort of reduce the load, but it's basically just find the intersects, call those out as potential data quality issues. And this would be a back-end spatial join, leveraging Apache Sedona functions and Databricks SQL. That, again, is a very good data quality control that we use in production on a daily basis. All right, and that's about it for the demo.